I would like to welcome you all and thank you for taking the time to join us today. I will first address some logistical issues for the session and then introduce our speaker, Rick Haynes. We have a lot of material planned for this one-hour webinar, so the audio will be muted for the remainder of the presentation to ensure that we are able to get through the entire presentation in the time allowed. We will not be able to hear you, but you will be able to hear Rick. Please do not let this stop you from sending us text questions through the system during the presentation. If Rick cannot answer your question either during or at the end of the webinar, we will either email you or call you with a response. There will also be a recording of the webinar available on our website within 48 hours. You will receive an email with a link to the recording. Please know that as a participant in this webinar, someone with Smarter Solutions will be giving you a call. If you do not want us to contact you, please let us know in the feedback survey at the end of this webinar. I will now introduce our presenter, Rick Haynes. Rick has over 20 years of Lean and Six Sigma experience as a practitioner and is one of Smarter Solutions' senior instructors. Through his career, he is certified as a Master Black Belt Champion, and a Yellow Belt, along with teaching and certifying professionals in all the Lean Six Sigma areas. His personal Lean Six Sigma work has spanned nearly all business types, including manufacturing, transactional, and research and development. He is a master degree statistician and has taught statistics in the Penn State University system. He has worked in all levels of the business, from entry level up to site engineering manager. His life experiences and skills will provide you with an engaging discussion. Again, thank you for joining us today. At this time, I will turn the presentation over to Rick Haynes.
Hello, everybody. It's Rick. We're going to be talking about something I have a real passion for today. And as Ann talked about the things about my history, it talks more about the Lean and Six Sigma stuff because I think that's what I do more at Smarter Solutions here. But my whole life in this world started after I got out of the Navy at Texas Instruments, so we started statistical process control. So a lot of the passion for this topic came out of my work back then. Let's go into a little bit of history. Now, if you recall, the title said 50 foot and 30,000 foot. We're going to use those acronyms throughout the talk to talk about 50 foot is really meaning you're at the ground level. I know you're not 50 feet tall, but you're at the ground level looking at an individual process, where the 30,000 foot call is like you're in an airplane flying and you're looking down and all you really see is a building. You don't really see a process anymore. So we're talking about the farther you get away from the process, how it may change the way you look at and monitor the process. Now, where did all this stuff come from, process control? I think knowing that the history of process control and control charts helps you really understand where we're going today. Oh, by the way, Ann had said, please type in questions on the GoToWebinar interface. We've already had one so far that asked about getting the slides from this presentation. Generally, we do not provide the slides. You get to rewatch the webinar. If you want something specific, contact us afterwards. We might be able to provide it. But on our free webinars, we generally do not give the slides out. So let's get back to the history. I think the first case of control charts was found with Walter Schuhart when he worked for what became AT&T, which was Bell and Western Electric, making telephones. He wrote a book in 1931 called The Economic Control of Quality of Manufactured Product. What he was doing is he was watching the manufacture of telephones and could see when there was a change to the process, the output changed. And he developed control charts as a tool to graphically identify when a change occurred. So he was looking for minor changes of a process so that the operator or the person running the process could change the way the process is run, an adjustment, a setting, or whatever, to return the process back where it needed to be. Now, it was mass manufacturing of telephones, and if you don't realize it, this is back when there was only one company making telephones in the whole world. So it was a big deal. They wanted to keep every telephone the same for interchangeability and all that, so that came up with control charting. Now let's look at what's called statistical process control, or SPC. Diving into the name, it tells you a lot about it. Statistical. Well, again, it's both hard to say, hard to do, and hard to learn, but it really means using the benefit of the pattern of the values, the distribution, to create control limits and rules. Process, it deals with a process. And for controls, I think that's the one we forget the most, it's for controlling stuff. Oh, it says the slides aren't changing. Is that better? I just got a note. There we go. All you missed was, I'm going to go up one. All you missed was this slide right here. I apologize, I got excited and didn't update them. But I really said all those words. Go to the next slide, statistical, process, and control. But again, it's about using statistics to monitor a process to determine control. Now, it uses control charts. If you have ever taken a statistical process control or control chart class, they gave you these charts. They taught about individuals charts, X bar and R charts, P charts, U charts, and a whole bunch of them. This roadmap of selecting was determined if you're going to use these charts to control a process. General format, they use control limits that we call 3S limits. I'll talk a little bit more about that later because they're not really 3 sigma. And it uses zone tests or pattern tests to decide when you have an uncommon or atypical point, which we may call out of control. Now, all a control chart really does is identify non-random events, or as I'll talk about in a little bit, non-homogeneity. So given all this, where should you apply SPC, or 50-foot level control charting? At a single process, when the goal is to trigger a process change or an adjustment when you see a change in the process, and you meet all the assumptions of the control chart. Now, I'll talk what they are further on. That's what we call the 50-foot level control chart. Now, when is it not appropriate to use SPC? Well, if you're monitoring a data stream that is really a combination of multiple processes, meaning 4 or 5 machines, a whole product line that's coming from different places, multiple people doing it at the same time, so it really is not time order data, it's just the next one off one of the lines. Monitoring that type of data, you don't want to use the SPC rules for picking a chart. And that's what I want to talk about, why the 50-foot and the 30,000-foot level view of control charting are both appropriate in the right place, but I find that most people weren't taught some of this. So now it gets to our first poll question. What I'm going to ask you is, how does your company use SPC or 50-foot level control charting today? I've given you 4 choices. Please take a moment, use your computer, and click on the screen. We're going to keep track of them here. Give you just a few more seconds to do it. But I want to know where your company is with SPC. Because at some level, knowing where you are helps me adjust what my topics might be. We'll give it about another 2 or 3 seconds. Please check off your thing. And Ann, if you would close the poll and post it for everybody, please. You should all see, well, I guess it didn't post, right? What we got here is, oh, there it is, hit share. All right, now you should see it. It's interesting. There's a little bit of everything, but charts are never used with the least of them. What we're going to get down to is most of them use charts on single processes, which is wonderful. What you'll find, those of you that are using control charts on multiple processes, the output from multiple processes, probably struggle with some of the examples we're going to cover later in it. So if you close it now, and we'll go back to the presentation. Now we may have an issue. We're going to get this out of here in a minute. I don't have it. We'll come back to this. Looks like we froze our screen for a minute. We'll be right with you. I'm not sure how to get back out of this one. Oh, here we go. I got it back now. I apologize for that mistake. Now we're back to the presentation. Process engineer. My life in this whole world that got me here today started as a process engineer at Texas Instruments here in Austin. I came in right at the beginning of a statistical process control implementation across the entire manufacturing site. At the time, I was assigned processes that were to be mined. I put the SBC together after a simple one-week class and attempted to manage the processes. I'll tell you, it was a struggle. Some worked, some didn't, never knew why. Through all this, I must have done good enough. I became the site engineering manager. I went up through a supervisory role where I managed everybody who did SBC management. Well, I still wasn't sure why some charts worked and some didn't. While I was there, I became a certified black belt in Six Sigma and a statistician. And it was really through the statistical training where I really understood why what we had done at Texas Instruments was not really the best way to go. We were using SPC in cases where it wasn't appropriate. At that point, I became a teacher and started teaching SPC and statistical methods in business. I kept in my Six Sigma, and now I'm here. But I've spent my whole career dealing with SPC stuff. Some charts for me, individuals charts, and at times an X-bar and R chart worked fine, but other times they were completely unacceptable. Now, what does it mean to Lean Six Sigma? Because that is one of the big things our company does, is teach Lean and Six Sigma skills. But the basic body of knowledge for Lean Six Sigma, for Green Belt and Black Belt, includes control charting. And it should include some level of SBC training in a traditional sense. The problem, until I arrived at Smarter Solutions, we always taught SBC rules for both the measure phase to get your baseline of your process and the control phase to control your process. Now, I know today that you should only use the traditional SBC in the control phase. When you're doing your measure phase baseline, you're not dealing with generally a process, you're dealing with a business process that's run by lots of people and potentially lots of equipment over lots of periods. And it is no longer to manage or to control a process. You're using these tools to observe the general performance and capability of a process. That's the 30,000-foot view of the process. You're stepping back at the business level and saying, I have a problem. So in this class, we're going to talk about why SPC didn't really work at the Six Sigma measure phase, or really look at the overall business process. In Six Sigma, what we do, and I remember the trainer saying it, and it still bothered me, but he goes, the process, yeah, it's out of control, but it really looks okay, so continue on, do your capability assessment. The statistician side of me says that's really a wrong way to teach people, but it was what you had to do because it was being taught. That was the only option of the student. Now, SBC charts are not inherently good or bad. They just are. But for 50-foot level process management and control, there are really a lot of choices, and that's what the Schuhart control charts are about. Boy, when you leave that, though, and go beyond it where you're measuring multiple process streams, multiple products, or a higher level of your business, up to even the enterprise level, that 50-foot process control decision tree that led you to a certain chart would lead you down a bad path. Really, we're going to talk about here the individual's control chart, the chart you got with one X at a time, is really the only appropriate control chart that you can use once you leave the 50-foot process control level. Otherwise, the control limits are not what they should be, and that's what we're going to be leading. So we're going to do a little overview of that. Now, why is it okay to only use an individual's chart? Now, you may have learned that this is an X chart or an X moving range or an individual moving range. Some level depends what software you use. Now, Excel doesn't make one of these on their own unless you know all the equations. It'll work with some add-ins, but we still recommend using real statistical packages such as Minitab or maybe JMP, primarily because they got a lot more help if you make a mistake. Now, the use of just the individual's chart for all of my high-level process measurements isn't new. It may be new to you, which I think we'll be talking about later in a question. But it seems like it really started with what Dr. Deming was talking about early in his career, about looking at the business as a system view rather than at the process or ground level. Dr. Don Wheeler, who's a prolific writer in this subject, statistician that I got to say also for his first degree at Texas here in Austin, but went on to work at the University of Tennessee in the 80s and started writing books about this subject because he found that most people in the world misused SPC. It had gone from what Schuhart had wanted to do, which was to manage a process, to people were using those rules on every data stream they found and really undermining the belief in the whole concept. So he started writing in the 80s about the advantages of an individuals chart. Now our company is run by Forrest Breyfogle, our CEO, another prolific writer of textbooks, books, and training material. But he started in the 90s really getting down and writing about why you really shouldn't use all these other charts and should use an individuals chart. Now, his view doesn't exactly agree with Wheeler, but each has got their own point of view. We really teach here Forrest's view, of course. It is now integrated into all the training we do. We've got an e-course talking about this. We also have the Lean Six Sigma courses. And what we're going to talk about at the end, resources, if you want to look this up, we've got a lot of articles that speak to it. There's other webinars that talk more of the mechanics, which I'm not talking about today. But it's all there. This isn't new. My estimate, and this is like all statistics sort of made up by my opinion, but about a third of all the statisticians out there fully understand this concept of what Wheeler and Breyfogle write about. But most people in manufacturing do SPC have never been taught it because they took a generic course from a generic book from probably an instructor that didn't really know what they were teaching and didn't know the limitations of Schuhart's rules. It turns out statisticians in an ad hoc manner knew this already and always used their tools right. I'm going to try to give you through this webinar examples why both methods can be right at the right place by looking at some common reasons or examples where a control chart using the SPC or Schuhart method doesn't work. So let's get to our next poll question. We'll be quicker this time. But this concept of an individuals chart in place of Schuhart charts, how does this compare to your prior knowledge of this topic? So you should please take a few moments and answer those questions. Is this really new to you? That's the 0%. Or 100% said, I've known this forever. Those are for the people that have taken our classes. You may have known it if you went to the University of Tennessee for any of their classes. And there's a handful of people out there that believe this. Let's see how it's looking. Oh, we got a good part that have heard of it. There must be participants in our stuff in the past. And the next one is, I've heard of it but don't quite understand. I think that's where honesty probably falls. You may have heard it, but you know something, until you really get down and try it, I don't know if you ever truly understand all this stuff. If you'd close the poll up now, please, and post the answer. I'll close. Share. You guys can see the answers. About a third of you put in, get it, don't understand it. About another third, I've known it for a long time, and we have a split for the rest. Well, I think all of you can take something away from this. Let's move on. So what is a control chart? I said the word earlier called homogeneity, which means they're homogeneous or all the data points are the same. I think that's a concept of control charting that isn't taught. I'm going to try to reinforce through this time. But generally a control chart has a middle line and two control limits. We consider those 3S limits or 3 sigma limits, even though they're not really calculated with a standard deviation. The reason we call them that is they're expected to be the boundaries of the data that you're charting in that 99.73% that you expect from 3 sigma from a normal control or a normal distribution. Now there are control charts for non-normal data, but the limits are created so that they bound that equivalent 99.7% of the data. What's not written, though, is all these symmetric ones, there's really an unwritten requirement, well, maybe not requirement, but assumption that the data is symmetric and relatively normally distributed so that the control limits fall in that plus or minus 3 sigma list. Now, every control chart was really designed to find process changes. If the process is running randomly and consistently, there should not be an out-of-control point. Well, that's not fair. There shouldn't be a random out-of-control condition except with a random probability, which would be just under 1%, but 99.7, so 3 out of 1,000 data points could be outside of the control limits and still be a random event. That's okay. Do we have a question? Let's see. It looks like we have a question. It says, wrote about more comments talking about this applies to their career, what they've been in manufacturing. It gives some perspective of real-time and test data versus fab tools. I'm going to wait on that one a little bit towards the end. So I'm going to talk through a couple examples. It'll probably be a better time to come back to that. Let's get back, but control charts find change. But this assumption, and I would assume everybody who's seen SBC knows the first part, but your assumption of homogeneity and randomness. And I find in my consulting and teaching, that's the biggest mistake in SBC or in control charting. A control chart should be created with data that all is expected to have the same mean and standard deviation. That the only difference in the data points is random variation, and each point has the same. Consider it like a residual plot on or ANOVA or a regression. They have the same mean and the same standard deviation on average. If you don't have that, you're out of control. Now that could be a mixture of a different process, the mean shifts, the variation changes. We'd expect that, but really most of the failures we'll get at is combining data that doesn't have a constant standard deviation. Rational subgrouping. I've always liked this one. If you think of it more of homogeneity or similarity in the numbers, it makes more sense because rational just means thoughtful. What you really want to do is when you're writing a control chart or picking the sampling plan that you will apply the data to a control chart, the goal is that you sample so the variation within a subgroup or what's used for the control limits includes all variability that you wish to consider as common. Think about that, all that's common. So if you sample every 10 seconds and then 10 seconds and wait an hour and another 10 seconds of samples, if it's one point at a time, you're accepting all the data over that period as common variability. But if you do a subgroup in a period of 10 seconds and wait an hour and take another subgroup over 10 seconds, any variation that existed between the sample points is not in a control limit and therefore would be considered uncommon and would create out-of-control conditions. And that's going to lead to the biggest issues we'll get to. So again, if you sample data that is non-homogeneous or doesn't have the same expected mean and standard deviation, you will have an out-of-control point. Now, you may not understand this. We may be back to that second one. I've heard about it and don't understand it. But this should be your biggest takeaway out of the whole concept of control charting. I will probably make it more real when we talk about the examples. Here's my first one. I'm going to give 2 examples of using an X bar and R chart that didn't work. Now, what is an X bar and R chart? It's where you take a group of data, some group of points in a really short period of time, and then at some period in the future, you take another group of data points the same size. With each subgroup, you calculate the average of all of them and the range, meaning max minus min. Those are the values that go to the chart. That's the X bar, the mean of each subgroup, and the range is the range of the average difference across each subgroup. Now, in this case, real one here, you're making aluminum foil. If you didn't know, they get big blocks of aluminum and put it through rollers to make it thinner and thinner. But they're trying to get a certain gauge or a certain thickness of foil. But it turns out in the act of roll-forming aluminum foil, it's always thicker in the middle than it is on the edges. It's the nature of the rolling because these big steel rolls deflect, they wear, but you get this. So if you were to measure the average thickness across the web or across the width, it'd be 2 thin edges and a thick center. Let's say we sampled 3 data points, and we're going to use that in a control chart to measure the ability of this process to generate a constant thickness of foil. Make sense? All right. So I took 3 cases. If I went to the 50-foot level or the SBC chart, it would say you have a subgroup of 3, use an X bar and R chart. All right. So I would take my 3 points, calculate a range and an average, and plot those. Now the control limits on the mean come from the range value, which is really coming from natural variation or a bias. And in this case, I'm going to go back a slide. The range in the values is not random anymore, is it? There's a randomness at each point, but there's a fixed difference in thickness between the middle and the edge. So I've created a bias. So my range now is inflated, not because of the variability, but due to this bow or thickness change. This would be the X bar and R chart that came from a random set of data. Now, what I did is I created a set of data with a random number generator, normally distributed, 3 thicknesses, and biased them up, the middle value up about 50% of the standard deviation range. What you see in this case is a little variation in the mean chart because the range looks good, but since the range is overinflated because of the bias, the control limits now are a long ways away from the mean data. This chart will never go out of control, even if the process truly did. Now you have a question, Ann?
I do. Various component studies should drive chart type and subgrouping sampling method, correct?
Okay, variance components. It's also called nested analysis of variance. It's a way that you look at a process to find where the components are in variance, usually in a hierarchical method. Yes, if you are trained at that level, which would probably be black belt level or better, probably mostly master black belts can deal with this, but what you can do is use that variance components analysis and capture where you have the most, how far you need to average across to get the subgrouping period. When we use this in practice, what we do is we really look over time. Do I want to do it average and an hour of data, a day of data, or a week of data, or a month? And that's generally the variance component method, is when we're subgrouping over time. Yes, it can do it. What you generally do is you would put the last significant variance source to be between the subgroups and everything else below it. Now, that may not be enough for all of you. If you do not understand what I said, don't worry. It's a very complex topic of using nested analysis of variance. But getting back to this chart, this is when you see an X bar and R chart with not enough variation on the middle. If you're a control chart nerd like I am, you realize that in 100 points you should have a couple of them near the control limits. There isn't here. This is a sign that you have a bias in your control chart, in your range, inflating your control limits. Now, the bottom, you can see the equations. Again, it's A2R bar to make your control limit. If the range is inflated, the control limits, get too wide. Now, what would be a better way to do this? Because really what I've done, I've combined data points into a control group, or the range subgroup, that are not homogeneous. Those 3 points, 2 of them have one average mean and one has a different average mean. It's that non-homogeneity that raised the range, which caused the control limits to be wide. So what might be a better choice? Well, one is you track the middle value, which should be stable on its own chart, an individual's control chart, then do the outer edges, which should have the exact mean and standard deviation. You can make a chart using that data. So you'd end up with multiple charts. What you're missing then would be the range across it. What if the bow or the shape changes? So you probably would then look at the range itself to make sure it's consistent over time, not using an R chart, but we'll see using an individual's chart. What we teach in our classes is what we call the 30,000-foot level view. We have a whole decision tree that goes along with it. But this would tell us that if you collected that subgroup data, don't give up the knowledge. Calculate the mean of each subgroup and plot it on an individual's chart. What's neat about that is it makes no assumption of the within subgroup variability that made it. It becomes a single data point that if the process is consistent, the overall mean should be consistent. We run it with an individual's chart. This allows both the variability in the short term and between sample points to be included into the variability and into the control limits. To ensure we cover the bow or the shape, we would also take the standard deviation of each subgroup, put it on an individual's chart also, and plot it. Now, I admit, small samples of 3, the standard deviation might be a little rough. Although we teach that, if you chose to use the range as an individual's chart, you could, but I would not use a range chart, because range charts are based on an assumption of range distribution, which would mean the control limits are a function of the average range. We don't want that. We want control limits that are based on the variability within the data we collected. So here's what it would look like in our 30,000 foot level method. You can see 2 charts. Upper one's the chart of the means. That looks like a really nice chart. There's points near the control limits. Most of them are in the middle. If I jump down to the one below it, just the standard deviations, if I look at that, again, most are in the middle, a couple near the control limits, and it looks fine. I did throw the equations in there. Again, in this case, if you look, the control limits are plus or minus 3 times the individual moving range average at D2. That means D2 over MR bar is really standard deviation. But now the moving range includes the variability between points because it's the moving range. We get a great chart. So here again, we're using the individual's chart, but measuring a process outside of the 50-foot level, we're taking care of the non-homogeneity issue here. All right. Next one, consider we're baking cookies. Now I know the question came up about design and tools. Let's get down to something simple, making cookies instead. You have a process that makes cookies. You make dough, you roll it out, you push it up, such as a cutout cookie, bake it, and measure the thickness. Well, that thickness tells you if I'm getting the right output, I'm getting enough cookie per my bags, everything looks good when I ship it, and I know my picture looks more like an Oreo, but it's the only one I could find. Our goal is to make every cookie the same with respect to thickness. Now, do I think there would be a variation within each batch? So if I rolled it out and started punching it, would there be variation within that roll? Well, of course. Some are thicker, some are a little thinner, but they're probably relatively consistent within a single roll. But the next batch of dough, I roll it out, I probably can't get exactly the same thickness. Now, within that set of cookies, they're probably consistent, but I would expect the average to be a little bit different than the prior average. So what I have now is consistency within a batch, but the mean is changing batch to batch. So how would that look if we did it with SPC or 50-foot level tools? In this case, we measure the thickness of 3 cookies per batch, randomly selected. Like I said, in this case, the mean's changing with each batch, but they're consistent within batch. This is what the X bar in our chart would look like. Now, if you have run SPC in the real world, you've seen charts like this. Now, there's a lot of red dots, looks like out of control. And again, this is made in Minitab. But doesn't it look like all the data does look pretty consistent over time? I mean, if I look at the white band, most of the dots seem to stay consistent. The process doesn't look to be drifting up or down. I want that chart to be in control because it looks stable. But what's really wrong? The range is very small because within batch is very small. And the within batch variability is what's used for R bar. And it's really applying those control limits to the mean. So if the mean changes, that's a non-homogeneity issue because the mean isn't constant in every batch, therefore it's out of control, which generally is not the goal of the person putting the control chart together. If you want to look at it one way, an X bar in our chart will be out of control if there is any variation source that does not exist within the subgroup. That idea of variance components that came up before, if there's a significant variance source that's not within the subgroup, you will be out of control. But I would look at that as still a relatively stable process. So what if we looked at it at the 30,000 foot level or used the individual's chart instead? So I've talked about this. What would be a better way? Well, let's take the mean of each subgroup again, put it in an individual's chart, and that's the one on the left. It looks fine. The process is really stable. It's got the same mean over all the data points and a consistent standard deviation. But if I look at the subgroup standard deviation, that's interesting. Oh, it still says I chart of changing mean, but it is the standard deviation on the right. It is also consistent and stable over time. This tells me that process is stable on average, so the average cookie thickness is consistent over time. and the variation within each batch is also consistent. So if I was to really draw this out, what I really have is each batch is a little histogram or a little bell curve, and all those bell curves pile together to get the overall process that I ship to my customer. So this IE 30,000 foot level method is really decomposing it. It's not making any distribution assumption or anything. It's just looking at, are the calculated values consistent over time? It's very powerful. So what did I really look at in both of those? And again, please keep typing questions. Do we have any coming in yet? Any good ones? Or should I wait till the end on them?
Yeah, we'll wait till the end.
All right. I appreciate writing in. We are not forgetting them. I'll cover mine at the end of the seminar. So that was about X-bar and R charts. I covered the two most common cases. You see too much and too little variability in each subgroup. Case, the mean is outside of the limits or tight and not even reaching them. Now, if I get the Forrest Breifogel's pet peeve, use of the P-chart. Now, one of the big ones we were taught, the boss always likes to talk about your defect rates in the P-chart because it's got a nice average defect rate in it. But in my history, I can't think more than a handful, 5 or less, times that a P-chart's ever been appropriate at any time I've ever used it in business or seen it from a client. One of my statistician friends jokes that the P and P chart means probably should have used an individual's chart. Well, let's look at this. I've created simulated data here that you're running a process line that has 3 different defects going on. 2 of them happen at 5% randomly in the process batch, but I have a 3rd defect that comes and goes. Say it's based on the raw material, it's based on the operator, it's based on the phase of the mood or whatever, but it's a problem that comes and goes by batch. It's very common to see this. But I have it created that 25% of all the batches have this additional defect in it. So I ran these all together, summed up the defective rates, and made a P-chart from it. So, but how does a P-chart work? What a P-chart does is it calculates the average defect rate, P-bar, and assumes that you have a binomial distribution, because the assumption is every item, unit, part has an exactly the same probability of being defective. That's what a P-chart's testing for. So it calculates the standard deviation based only on the average defect rate. Now, if you really don't have the same defect rate on every item or defect probability, you will have an out-of-control chart, and that's why they're always bad. In this case, I had a defect rate that was increased in 25% of the lots by an additional 5%. So are those control limits on a P-chart really at plus or minus 3 sigma equivalents? And the answer is no. It's only true if it's a pure binomial distribution, which means one defect rate and each item has exactly the same probability of being defective. So here's my chart. In this case, I have 3 out-of-control points on my P-chart. Well, it turned out that those are the three of those lots had high defect rates in them. But what you may not see, and there's 25% of those dots or lots have the extra 5% impact on it. I think I used lots of 100 to make this. But it turns out sometimes the extra defect cost may have added nothing. Maybe it added 1, but every now and then it added a lot, it became out of control. I bet you can guess where I'm going. Now, I look at this chart and say it still looks consistent over time. So the question, is it out of control or is it not the right chart? We would say you should really step back and use that 30,000 foot level method, because this isn't managing a single process through a single line where you have homogeneity or homogeneous pieces that every part has the same defect rate. If I put this data on an individual's chart, you can see it here. The process is considered stable and in control. There's no out of control points. Now, you can pick on me for some other things. That may be a slightly skewed distribution, but this would say it's acceptable. Now, if you've used P-charts, and if you want to flag a little note in there, you may have also seen this type of thing, that P-charts are always out of control. We always just explain it away. Well, well, that lot just had a high defect rate, so that's what happened, and you say, oh, okay. But in reality, chances are you did not meet the requirements for the P-chart limits to be 3S limits, which is homogeneity. The last example I'm going to have, and then we'll dive into questions. Non-normality. Well, non-normality does happen out there. So I got an example. We're going to talk about measuring the time to do something. But all these Shewhart SPC charts have a bit of a distribution assumption that's unwritten with them, being a normal distribution. Now the P chart really has a binomial, and if you use a C or U chart, it's a Poisson distribution. But we don't consider that. In my original SPC training, nobody talked about anything but normally distributed data. All our examples were normally distributed, but no one told us. So we're going to look at, in this case, what if there is a non-normality in the data? What would that do to your control charting rules and the Shewhart SPC or 50-foot level stuff? Consider we're tracking a process over time, repetitive task, takes about a little under 10 minutes to do the task. It doesn't really matter who's doing it, what day of the week, what time of the day, what month we're in. It just takes a little under 10 minutes to do this task. But we are measuring the duration of time, so we are tracking the time that does the task. What do we know about that? Well, time must be greater than 0, because if it did the task, it must have taken some time. And generally, when you have a problem or a new person or something isn't exactly right, it hardly ever goes quick. It generally goes long. So what I have here is 100 data points. And you can see it's skewed to the right, numbers up to 50 minutes. And there's some short ones, too. So let's follow that. That's one data point at a time. I time one transaction every half hour, let's say, and plot it. Here's my chart. Individuals chart, one point at a time, but notice I have 4 out-of-control points. Now, we see this all the time when we're measuring business processes. Now, the question is, are those out of control, or is there something wrong with the limits not being at exactly 3S? Now, if I look at this, I notice there's point in time. There is nothing low, is there? My lower control limit's at minus 16. Unless you're doing quantum mechanics, you can't have negative times. It can't show up before you start. So in this case, part of with the range that seems allowable within 3S limits really can't exist. So there's something wrong. That control chart is not giving me a signal of an out-of-control point. What would we do? Well, this is time I said, a negative lower control limit, and there's a natural limit at 0, which we know from looking at the data. So again, something's wrong. What we would tell you to do is, that's a skewed distribution. The control limits on an individual's chart are really based on somewhat of a normality. What you do is you generally do a transformation of the data. In this case, I used log normal data, so I took the log normal transform. In this case, it's a box-Cox transform with a lambda equals 0. But it's really the natural log of the data, then plot it. What I've done is really created a data set that is now passes a normality test. When I put in the individual's chart, it looks random. Therefore, I'd say the process is stable. It wasn't out of control. Once I get a chart that these limits are really the equivalent of 3S, so there's no out-of-control points. Now, this is probably the biggest black box in the 30,000-foot level method to people. But when you play with it and try it, you will find that if you really have an out-of-control point, if I'm going to go back a slide, or if I go back to this slide, if those are really out-of-control points and not random events, you can't transform them to be normal. You can only use a transformation if it is truly random data. It works when it's random but not normally random. So again, we say this process is truly stable. So what's the question? The chart was wrong. Those were not out-of-control points. It was an inappropriate control limit. Let's go back to the real purpose of this whole seminar. 50-foot versus 30,000-foot. With these 4 examples, I really poked holes at why the SPC or the 50-foot rules don't work. And they work for some common reasons. The data wasn't homogeneous. All the data didn't have the same mean and standard deviation. With examples in X bar and R charts where either the subgroups had too small of variability versus the mean changes, or they had a bias that were too large. In each case, it didn't work. Why? Because the control limits are based on the short-term variability, not all of the common variation in the system. And that's why we, again, like the individuals chart, because it takes into account the variability between samples into the control limits. And the last one, just because you pick a control chart that they told you had 3S limits doesn't mean they are really 3 sigma limits. I don't want you to give up on common SBC, because those tools really are wonderful for managing a process. So where can I use the 50-foot charts? Or what Schuhart would have taught us? Well, if you're measuring, like an example of a dimension on a product that's being produced on a single machine, you could use an X bar and R chart or an individuals chart. But when you see an out-of-control point, the operator will adjust the machine back to nominal and let it go. That's where the SBC charts were intended for. On a single process with a single execution, that when you see a point, you immediately control the process. Another case could be, you're looking at defect occurrences. This is more of the P chart case. You're measuring a single product line on a single process, and you're charting each individual defect caused on a P chart. Not the sum of all defects, but you really can only get by with a P chart if you're measuring only the rate of a single type of defect. Now in business with normal quality, you don't have defects in every lot, so this really doesn't work because every lot doesn't have at least one defect. So it gets to the point that the P chart is never really good in normal life and in production. It's really a statistician's tool to use in an exam. But the point is, these methods work when you're using them to control a process. Don't use the 50-foot or the SBC tools to monitor a business process or an enterprise process or using scorecards. You will lead to problems. Last poll question. We finish up, we'll answer all your questions. In which of these examples have you seen within your business? And these are the 4 examples I just gave. An X bar and R chart with excessive subgroup variation, meaning the mean chart's tight to the limits. X bar chart with excessive variation of mean, so one when it was always out of control with real tight limits. The P chart that doesn't work, or skewed data in a chart. So please choose to answer them. Again, I think you can pick more than one in this one. Got a few seconds here, and we'll close this out and post it for you. If you would close it now, and we'll post it up for everybody. Share. If you look, non-normality seems to win that horse race. You know why? Because they never taught us that stuff in SBC class. It tears me up the times I've struggled with that. It also is one of the biggest causes for firefighting. Or if you chase down every one of those out-of-control points and they were really random, you tampered with your system. You caused more variability. The next biggest one was excessive subgroup variation. I find that's a huge one, really because you are taking this for quality control, your sample plan. You want to make sure that every point's in spec, and then apply it to an X bar and R chart because I already have the data. But you know there's a bias in that data, so don't make a control chart. You're better off to condense it down to a single data point out of each sample, or use the 30,000-foot level method. Thank you for that. Now if you go back to the slides. All right, we're wrapping up here. How do you choose your best method? The 30,000-foot level method is best used for turning data that comes from more than one process, machine, or location. We consider this the Deming view of the business, the system view process. What I really like about these methods that use an individuals chart is you're really treating the data as that way your customer sees it. It doesn't know what person, what line, or whatever, just the parts are coming out of a black box meaning your business, and you're charting them that way. So that's what you look at business and system level. The SBC or 50-foot level SPC methods that you were taught are really only applicable at the 50-footer process level when you are charting a single output from a single process with the intent of making changes in the controls of your process. That's the Schuhart or process view of a business. So think about it. The higher level ones, the system view. The SBC or 50-foot is the process view. It's exciting when you actually learn this. Now, we were asked for slides earlier. You have some resources for this. This presentation really didn't teach. Hopefully I've made you excited or gave you an incentive to learn a little bit more. There's a couple places you can look for stuff. You can buy your Forest IEE Volume 3 textbook that we teach our Lean Six Sigma classes over. There's about 12 chapters in there that talk about the appropriate application of control charts and stuff. There's many free articles that you can pull off our website if you log on. You can't press on this link that you see, but if you go to our smartersolutions.com and pick our resource library, or it's called articles.php, and when it has a search, put control charting in, and you'll see a whole series of articles that actually teach you the ins and outs of doing that. Or you can just call us. You will get, if you make sure you don't check the box that says don't call me, we'll give you a call. We also have an opportunity now. We actually have created an online training course that before this point has been only given to our big clients. It just talks about the control charting piece for you to learn it yourself, and we're selling it now. If you're interested, ask Becky when she calls you or whoever does reach out to you. And of course, we've got a lot of Lean Six Sigma classes you can take that also teach it. So again, before I summarize it, let's get to the questions we have right now. I'm going to go through them right here and see what we see. I guess I'm going to go backwards because, we got a couple of them here. At the beginning, you stated the control limits are approximately 3 sigma. Why is that? Well, what I consider a 3 sigma limit is you took all the data points in the control chart and used Excel to say what's the standard deviation, all that data, and multiplied it by 3. That would be an actual 3 sigma limit of the data. But in control charting, we never do it that way. We use a range chart to estimate the standard deviation, plus or minus 3 standard deviations of the data in the ranges. So we call it an equivalency because there may be a variation source that's not in the range that is in the data above, such as the mean or the X chart. And that's why we say approximately. Next one said, we did the variance components one. The opposite of the aluminum example said could be wafer site data, where you measure 9 sites, again, probably all the corners and middle and then the center. Use the X bar and R chart would say your process is probably, since you would have a bias in the thickness, the middle being a different thickness than the edges, you'd get a similar case to my foil, which would say that the means are always tight to the chart, don't reach control limits, and you probably would be very slow at detecting process changes. That is true. That would happen. Thank you for the example. I got a couple of them here. Back to slide 35. All right, let me go back to that. If you didn't know about PowerPoint, you just hit 3.5 and enter, and it jumps back. Now, if I look at that, what was the question on that? If you look, that's what non-symmetric or non-normal data looks like in an individual's chart. If you can picture, visualize yourself looking at the side of your computer screen and looking down that chart, picture the histogram. Again, what you see is a big hump right near this middle area where it's around 0 to 10 with a long tail going out the high numbers. That ends up being what we had earlier. But when you see a non-symmetric or a skewed data, an individual's chart won't work because the control limits are built symmetrically about the mean. I hope that answered your question. All right, what do we have here? Some more? The key, a lot of people wrote notes. Not really questions. Thank you, sir. You said, thanks a million for that answer, and that always feels good because I'm talking to the wall. It's hard to know that you all are actually listening sometimes. Someone wrote here, someone that I know, that an individual's chart can trace back to Abraham Wald and Edwin Wilson. I didn't know that. That is, it could be true. I just know the first published works on statistical process control did come from the book by Schuhart in 1931. Another person here wrote, we didn't talk about capability indices. And no, we didn't. We didn't have it in our body of knowledge for this one. But honestly, you shouldn't do capability reporting until you have a stable process. The problem is if you pick the wrong chart, obviously it may look out of control, which means you shouldn't report capability, but you know it should be because it looks consistent over time. If you could see see me right now with your webcam. When I look at a control chart, I don't care if it's out of control or not, I put my hands on either side of it. If it looks like I can bound the data with a straight line over time, I believe it should be stable, and I must have chose the wrong chart. So that's usually my eyeball view of looking at it. Another question says here, the key to what engineers need to respond to common as well as special causes. It's an interesting question. Control chart's purpose is really to only differentiate between what's common cause, in control, and what's special cause, or out of control. Now, Deming would say special cause is an external fleeting event of the system. And that's what the 30,000 foot of the individual's chart view of control charting is. Because there are changes within a process, how you define them as common really matters. Such as changing a batch of raw material, changing an operator, restarting a piece of equipment. Those are true process changes. In the Schuhart view, or the SPC view, that's a significant process change. It would drive the process potentially out of control. You would adjust it back to the nominal. In the Deming view, we would say changing operators, changing raw material batches, changing people, restarting the machine, that's part of our managed business. We have to allow that to change to do our job and ship stuff to our customer. He would define that as a common cause event. And that's really the homogeneity issue, and this idea of a control chart with an individual's choice is that you are defining those changes as common, therefore you do not want them to drive you out of control. And that's what I mean. There's two different views of control charting. It's not just common and special. It really, you get the choice of deciding what is common and what is special. What I did miss is Schuhart didn't call them special causes. Schuhart called them assignable causes, meaning that I could assign this change to this output, therefore it was correctable. Deming avoided the assignable issue because sometimes you don't know what the cause is. It's just an out-of-control point. If you've combined a lot of lines together, processes and product, you may never put your finger on when it happened or what it was. That's why he just called it special. Other questions? Are we getting close? We still got a little bit more time. I'll scroll through these. Someone listed Dr. Montgomery is another believer in this individual's chart, another statistician. Oh, we got a question here. Oh, after the transformation, the lower control limit was still negative. That goes back to slide 35. Probably it's still on your screen. If I go to the next slide with the transformation, you'll notice there is a negative control limit. But in this case, I've taken the natural log of the data. If you don't understand natural logs, a negative value just means the actual number is between the value of 0 and 1. Because a natural log of 1 equals 1 in the original data set. So yes, negative numbers are okay after you've taken the natural log of the data. And the next one says, what SBC rules do you usually use on 35 or 30,000 foot individuals charts? Run rules probably. That's a tough one. Those run rules, now I don't have a slide to talk about them, but what the run rules are, you may have learned them as Western Electric rules. Run rules, zone tests are also another word. What they do is they divide up the difference between the control and the mean into 3 sections, and we call those, they're really limited to 1 sigma, 2 sigma, and 3 sigma lines. We're looking for probabilistic patterns. In other words, if it is normally distributed data, some percent of the data would be between plus or minus 1 sigma, around 68%. But you can estimate the probability of any data falling in each of those 6 zones and outside of them. What you look for is patterns in the data. If they occur in a zone at a higher or lower frequency than you expect, you would say that's an out-of-control process. Now what we're doing though is these are really distribution tests. The more normal your data is, the more those rules work. If you really have a mixture of data, such as a bunch of batches that have slightly different means, but you roll them all together, you're going to have problems with all those zone tests because you really have a mixture of a bunch of small distributions that are effectively normal. So my advice to you and to really anybody using control charts is only add run rules for zone tests that are specific to the expected failure mode. If you expect the process will drift when it fails, only add a rule that is sensitive to drifts. If you believe the process will take a big shift when it fails, only add a rule that is sensitive to shifts. It's never recommended to add all of the rules, because now each rule has a false detection rate. The more of them you add, the more fraction of your out-of-control points are now false positives, and you end up chasing your tail all over again. So really minimize your run rules. Always use Rule 1, the out-of-control point, but I would probably never add more than 1 or 2 of the other zone tests or run rules, and only one that's specific to the expected method of failure of my process. Let me see what we also have here. Any more questions? This is the most questions I've got. This is wonderful. Someone said, thank you. I appreciate it. More people talk about run. There's lots of run rules out there. There's generally a standard of 12, I think, that I've seen. My favorites are the 2 out of 3 in Zone A, I believe. I got to get the zone numbers wrong. Or the ones people mostly like, so many above or below the mean in runs. It's usually 10 or 11, and then a run of a series that are all increasing or decreasing. But I'll admit I don't memorize them. I look them up every time I need them. Let's see. Thank you. One says, define an individual point on a P-chart. Generally on a P-chart, every data point is the defective rate of a batch or a lot. So it's just a percentage of the number of parts that are generally good or bad, doesn't matter, based on that lot size. Same as a P-chart would do. You just instead calculate the defect rate and plot that point and put it on an individual's chart. Let me get back to the end of my presentation here. By the way, all of you signed up for this. You can all email me at rick.h, Rick Haynes, my last initial, at smartersolutions.com. If you have additional questions, I'd love to answer them. I also write a blog that I put out based on student questions and what people write me, and stuff of general interest to people that have a Lean Six Sigma background or are just interested in process improvement. Along with this webinar, we are offering a series of books. Volume 3, which is one of these 4, is the one that the material that really speaks to the differences in control chart is available. It's a wonderful reference book to any Lean Six Sigma trained person because it covers the entire DMAIC with all the soft skills. Great book. It's also, if you have seen Forrest Breifogel's Implementing Six Sigma, 2nd edition, this is really the next book that was, he made enough changes from that, he renamed it. So it really is the follow-on to that real thick book. It actually involves more lean and a lot more soft skills into it than the Implementing Six Sigma book. But along with this are a book on how to apply these rules to manage a business, and then a couple nice, easy reads about the overall system. But you can get half off the retail price using this code that's listed on the bottom before the end of the year. Get yourself a Christmas gift using your company's money. Just order it right up. Are there any more questions? I guess that's my next thing. I think we're wrapping up. Someone wrote in about individuals and IMR charts. Here, there is a school of thought that says the individual moving range chart, since really the moving range is the difference between sequential points, it is so commonly, in other words, it goes out of control almost the same moment the individual chart does. That there's also, it's duplicative to show both. Many of us just quit showing the range chart when we display it. It makes it easier to explain to others. Even though the range is still calculated, it's just we don't show that chart, and that's why I showed you mostly just the individual's chart. The moving range was calculated in the background and not displayed. I guess that's about it. I really appreciate you listening, and you don't realize how much I appreciate all your questions. It makes it funner to do this right now. We got one sneaky last question. We use an exponentially weighted moving average chart. and heavily adjustment algorithms. Wow. Exponentially weighted moving average charts, and someone also asked to see this slide again. They're wonderful in some cases, but you would generally use those more in a known drifting process, in grinding and tool cutting, because you're trying to look at the drift of the process to make sure that you're keeping it adjusted to average. It's not a real standard Shewhart control chart, because there, at some level, is not the assumption of a constant mean in an EWMA chart. So really, they're used for a slightly different process, and I didn't discuss them. If that is the right chart to use, I'm not sure if an individual's chart would ever do you well. It really is a different type of condition. I guess that's about it. Thank you, everybody. We just went 5 minutes over, so I appreciate your extra time. Thank you very much. Once you exit this webinar, there will be a feedback survey. Please fill it out. If you have additional questions, put them in. And if when I scan over everything and find one that was missed, I will email back to you. Thanks a lot for your time.